Okay.
All right. Hi, everyone, and welcome to this talk that I think we could almost do in French, given the audience. But now let's do it in English. So thanks, Victor, for talking to us about category theory.
Yeah. So thank you, Philemon. So yeah, my name is Victor. Today I'm going to be talking about applied category theory and more precisely something we call graphical calculus. So yeah. So you just left, but I wanted to say thank you to Philemon for organizing the ZUCMAP. I think it's kind of cool. I don't usually come, but I watch the recordings, and I think it's a fun way to talk about some interesting math without it having to be too formal. So, funny story, we actually studied together in the first semester of mathematics with Philemon, but I failed. So then I went into communications engineering, and now I'm in electrical engineering doing my master's here at ETH. But as you can see, like I always kept kind of a thing for math, not too formally, but I still appreciate it very much. So, which is why I'm here talking today. So, like I said, applied category theory. Some of you who have already touched upon it may think that those two words don't belong together in any shape or form because category theory is way too boring, way too long, and too abstract. Structures are pointless, and we don't know how to, there's no use for them. Well, for that, I would say give me about like 40 minutes, and I'll try to convince you otherwise, and if you're still not convinced, then we can talk about it later. But let me make my case. So, yeah, category theory, some of you have never heard about it, maybe? Have any of you not heard about category theory? All right, so I'm going to give you a quick informal recap. To me, category theory is cool because it's like a different flavor of mathematics, because mathematics, you always try to look really precisely into detail and observe smaller and smaller structures that are more precise and more precise. And it's very much like psychology, where you hone in to one specific person and you cater to their problems. Category theory does the exact opposite, is we look at larger and larger objects and we try to create relationships, much like social science. And so it gives you a different way kind of to think about things, and what category theory does is it observes relationships between mathematical concepts. So if you've ever noticed that some things are kind of uncannily similar between, let's say, algebra, geometry, analysis, then this is exactly what category theorists do. And that is a first reason as to why it could be applied. It's because engineers who are known for not being very good at any particular domain of mathematics, we have to deal with a lot of easier problems in mathematics, but coming from a lot of different topics. And so if with category theory, we can create a framework to connect these topics, then we could hopefully find a way to make it useful for people who will put these topics together. So that's a lot of rambling, a lot of ranting. I'm going to get into some definitions, so we start. This is one of my first times writing on the blackboard, so I thought I'd write it on the blackboard because, as you'll see, we're going to do a lot of drawing, so it's kind of cool. I thought it'd be fun to do it on the blackboard, but tell me if I'm writing too small, okay? So the basic definition of a category is what we're going to start by working with. And a category, which we denote curly C, like this, is an algebraic structure which is comprised of four things. A collection of objects that we denote ob-C. And note that I'm not saying a set, I'm saying a collection because we're keeping things very general, and we'll get into examples and details later. We have a collection of objects, and for any two objects of C, we have something called morphisms from X to C. So F is a morphism from X to Y. We denote it like this, so we could write it like that. F is a morphism from X to Y if we can connect X and Y in a certain directed way. Notice that this does not mean that F relates Y to X, nor does it mean that X and Y are relatable only via F. So that means that we have x here, y this way, and f is like this. This is how we're going to draw it. And like I said, it's not necessarily unique, so that means that there could be multiple paths, like G or H. So this is object morphisms. And then what we have is we're going to have something called the composition operation, which we're going to note as a semicolon. Sorry, that might be a bit small. Semicolon for any triple x, y, z. And what it does is it takes a morphism from x to y, a morphism from y to z, and I'm sorry, I'm trying to keep some space, and then it returns a morphism from x to z. So that may look like a mouthful, but it's not very complicated. Well, the way we're going to do this is represent three objects like this. Say we have f from x to y and g from y to z. And what this does is it guarantees that we can just hop from x to z right away via f semicolon g. So here you already kind of see what I mean by maybe observing larger structures and reducing detail. It's because we're kind of skipping this intermediary step of y. What we're going to do is instead of observing f and then g by stopping at y, we're just going to go from x to z right away by composing things. So lastly, what we need is something called the identity morphism, which is defined for every object x, and we write id subscript x, which just goes from x to x. Again, this is maybe not very intuitive what it does, but to show you how it is intuitively, if x is an object, then the identity morphism just loops over the object. So we have these three components. We have collection of objects, collection of morphisms, the composition operation, and our identity morphism, which is nice, but these always have to satisfy a few things, obviously. So what these satisfy are associativity. So this has to be associative. So we need associativity of the composition operation, which means that if we add another object here, u, and we say that h goes from z to u, then doing fg and then h is the same thing as doing f and then gh. So what you can think of is just you can shift the brackets between the priority of these two. It's the same thing in the end, okay? It's like, yeah, if you stop at z and then go to u, it's the same as stopping at y and then going directly to u when you kind of reduce these stopping details. And lastly, we have something that's called unitality. And that's not very straightforward what it means, but what it actually means is that for f from x to y, I'm just going to keep saying that f is from x to y because I don't want to write this all the time. What it means is that if we take the identity of x, compose it with f, it's the same thing as just doing f, which in turn is the same thing as doing f and composing identity of y. All right? So again, this is not very intuitive, so what I'm going to do is make another picture for you. And what this means is that if we take x, y, and we write this, we have the identity of x, we have y, and the identity of y, then kind of looping over x and then going to y, when you zoom out, is the same thing as just going from x to y. And similarly, going from x to y is the same thing as going to y and then just staying at y. So this is the definition of a category. It's a bit lengthy, and I'm sorry, but this is kind of what you have to go through to first understand what it means. And then we can go through a few examples. So maybe this has been a bit like intuitive on what it is, and a very simple example would be sets. If you consider that objects are sets, morphisms are functions, this is simple function composition, and this is the identity function over the sets. Well, we get associativity for free, and this holds quite simply, okay? So that's a very canonical example that we're going to try to keep on using throughout this presentation. But we can also, another very simple example that I'm going to use is vector spaces. So if our objects are vector spaces, morphisms are then linear maps, which we can compose in associative manner. And if this is the identity map, or the identity linear map over the vector space, then we get unitality as well. So there, we've shown very basic things that are kind of intuitive, but let me show you something a bit less intuitive. So what if we have a category of cities and trips? So I'm going to use this other one actually. If we consider that objects are cities, like London, and then we have Paris, and then we have Zurich, obviously, then these are our objects. And what if we take a plane from London to Paris, right? And then we take a plane from Paris to Zurich. Then if we take these two flights one after another, it's kind of the same thing than going from London to Zurich in the grand scheme of things when you just think about it. Similarly, if you take a bus within London and then fly to Paris, you just flew to Paris, effectively. And if you go from London to Paris and take a bus within Paris, then you've effectively just gone to Paris. And that's exactly satisfies the conditions of a category. So we've already created something very applied, which is a category of cities and trips. And we see now that category theory actually formalizes our way of thinking about how we can compose things together, okay? So I'm going to take another example, which is going to be our last example before we get into other things. It's in the domain that I'm actually specializing in right now, which is information theory. And in information theory, we study it's a branch of probabilities, and what we do is study mathematical information and transmission of that information. So if you know engineers, then you know we like to draw things. We don't like to write equations. We like diagrams. So what we do typically in information theory is we have this sequence of boxes, where you take a message M, you encode it to, say, bits, and then you transmit it over a channel, this is a small channel, and then you get Y, because the channel may not be perfect, so you maybe don't get X again, and then you decode it, and then you get M hat, and you hope and pray that M hat is the same thing as M. So that's a bit aside of the point, because this diagram here is making kind of bold assumptions. And this may ring a bell with regards to what we just saw. And the assumption that we're making is that the output of this encoder is the input to the channel, which means that we can consider this big box, and then we get encoder composed with the channel, which is a transformation or a morphism from M to Y. So we see that the simple notion of a category is enough, quote, to describe these series compositions, right? Which is a very prominent thing in engineering. And this is now the main part of the talk, is what I'm going to do is we're going to construct the structure. That sounded weird. We're going to build the structure that can describe, hopefully, any engineering diagram. The idea behind this is that we want to create a visual language, so be able to draw things, but that the underlying the principles underlying it is mathematically rigorous. So you can actually draw your proofs now. You don't need to you won't be, it won't be necessary to write out the equations because they will be, they correspond to a diagram. So are there any questions on this so far? Okay, cool. So recap, category. We've seen that the category can explain these diagrams. So just a quick recap. What we did is we had points and arrows here, where arrows are morphisms, points are objects. But in these diagrams, we're doing it kind of the opposite, and I'm sorry, there's no better way to do this. And so what we're going to do is start denoting our objects by wires and our morphisms by boxes. So yeah, our category formalizes this, and we've seen series composition. Now, if you remember high school, you've probably done some electronics or electricity stuff, where there's not only parallel series composition, I just spoiled that, and then there's parallel composition, like this. And we want to be able to draw this because in engineering we're always computing or processing things in parallel. It's much easier. As long as these don't interfere with each other, then why not do them at the same time? So how do we kind of represent this with a category? Well, to do so, we would need to add some extra structure, because what we want in the end is to be able to combine this into one morphism like this, right? Because we want to reduce the boxes always, kind of taking a step back. And what we need to do is consider these two guys here as one object, so it has to still be an object of the category for this to work, the output as well, but this also has to be able to be like stackable. You want to be able to stack these vertically. And this is what we do. What we do is we're going to give a monoidal structure to the category. Now, what does that mean? It means we're going to define something called the monoidal product, which probably more familiar with it than I am. But what we're going to do is add this monoidal product, which takes... This means that we're taking two objects from the category, combining it with the monoidal product, and we get one object from the category. Just like, let's say you're taking reals and you multiply them, then you still get a real number. So this is the same thing, and this notation means that if you take two morphisms and you put them together with this monoidal product, then it is still a morphism, but between the monoidal product of the inputs and outputs. So with this, what we also need is something called the monoidal unit, which is an object of C, which satisfies this. So it just means that doing it on the left or the right of A, for an object A, I'm not going to write that down, is just the same thing. So with our reals example, then it's just 1. With multiplication, you can multiply 1 on the left or right, and you still get the same number. So this is our monoidal structure. And now that we've used this monoidal structure, we can properly define this thing, where it goes from x1, cross x2, and then you get f cross g, and you get y1 cross y2. And we can reduce this even further now to this. F cross g, x1 cross x2, y1 cross y2. So now we can collapse our morphisms from the horizontal perspective, as well as we can stack them on the, vertically. And what this does now is it allows us to actually write bigger diagrams. So if we have something like this now, that takes two inputs, and you slide this one down, and you have... So this now is, we can write it unambiguously because of how we can compose these morphisms. So let's say we have A B, and C. And here we have A, B, C, D, E, F, G. Let me just, that makes sense. So what we do is we first consider these boxes like this, and this is just A cross B. And now this box, what are we doing here? We're doing the identity morphism because we're not changing anything. So this is just identity of D cross C. And now we have these two boxes here, and we just compose them horizontally. And what we get is that this is our total morphism for this very general diagram. So what we have here is a strict monoidal category, which is, again, the category, the monoidal product. And we can describe series and parallel composition, which is kind of cool. But we encounter a problem when we want to be able to cross wires, because this gets a bit problematic, and we have a morphism that does this. If we have x, y, y, x, and if you think about it kind of with strings and wires, if you cross things one way, you can either cross it a second way and it's untangled, or you can kind of commit to it and cross again, and you're even more entangled. And this is a big problem for our string diagrams because we get a bit confused, like, do we write things this way or do we write things this way, right? This is a bit confusing. So what we're going to do is define something very much simpler, and which is called Abradingmorphism. And I'm going to put it on this one right here. So what we're going to do is define Abradingmorphism, which takes x cross y, and it returns y, sorry, that's really ugly, x. And we're going to denote it sigma xy. Quite intuitively, it goes from x cross y to y cross x. And what it does is takes this and it returns this object. So that's very simple. But like I said, we get a bit confused with this whole like overlapping, underlapping thing. So what we're going to do is we're going to have it satisfy three things. Notably, the first thing is called naturality. So this braiding morphism has to satisfy naturality, which means that if we're taking F and G, and then we braid, then it means that we can, it's the same thing as braiding and then applying FG. This has to be equal. This is not like anything you want to prove, it's just something you have to, it's a structure you need, okay? And what this means is that you can kind of slide these morphisms across the braiding and not get any problems, which is kind of nice because this just feels right. It kind of feels like it should make sense. And the next one is the big one that also has to make sense. It's called symmetry. And it means that if you braid once and then unbraid, or braid twice, then this is equal to doing nothing. So if we write this like this, we get that braiding xy composed with braiding yx is equal to the identity of x cross y. This is our second condition, and our last condition is nesting, because we need to consider the fact where we would maybe have a braiding of an object and a product of two. What do we do here? How do we treat this case? Well, it's kind of like if we had this, which is kind of annoying because it's not very clear how we're supposed to treat this. And what we're going to require is that this is the same as braiding once and braiding twice, like this. And so we would get x, y, z, and we get y, z, yeah, we get y, z, x. So these are three conditions for braiding. So what we've constructed so far now is we have a category with a monoidal product, and braiding that has to satisfy these three conditions. And these three things build what we call a symmetric strict monoidal category. And this is already something really interesting because any diagram with braidings, parallel stackings, and series composition can be described with this symmetric strict monoidal category. So I've been talking a lot about this stuff, and let's maybe put this to use, because that would be nice. And we're going to draw a diagram and see if it works with the basic example like a set, okay? So, right, let's write out this diagram. We have something right here. We have a morphism right underneath, taking two objects, feed this wire here, and then we braid these two. So if we get A, B, C, let's write D, E, F, then here we get F, E. Is that right? Yeah, that looks right. Okay, so let's cut this up. As we said, we can cut it up this way. First, and this one is basically identity over A cross F. This one is G cross identity over E. And this one is just sigma F E. Now, do we get any problems when we're dealing with this thing? Does this actually work? Can we compose this? Let's see. This morphism goes from A to A cross B cross C, and it maps to A cross D cross E. And this one takes A cross D cross E, and it returns F cross E. And now let's assume we're in the category of sets because it's the most basic example. We would want that to at least work, right? Does this work with sets? Can we compose this guy with this guy? The answer is no, because these are not equal. This is a big problem because these sets, if you consider the monoidal product to be, say, a Cartesian product, then what if you have A cross B cross C? Then that's not equal to A cross B cross C, right? But it's very obviously isomorphic, but it's not equal, so we can't say that we can compose these if our monoidal product requires equality. And that's exactly what we're going to do, is we're going to relax these conditions of equality so that we can compose isomorphic objects. So, this is a big thing also in category theory, is what you do is you try to not think about equality, but about isomorphism, which is also in this picture of taking a larger view on things. And if they look the same, then they don't have to be the same, but we can actually treat them in a similar fashion. So here what we're going to do is that to solve this problem here of not having equal objects, we're going to require that this guy, sorry, that's really bad, is isomorphic. So we have 1 cross A, isomorphic to A, isomorphic to A cross 1. Obviously, with that comes a little problem, because how do we treat the case of going from like this or this? How do we actually write this out now, because we have basically two wires and we have like 1A and we're trying to go to A. Well, it's very easy. What we define is that for every object A, we have this thing called a left uniter, sorry, and a right uniter, which are isomorphisms. And now this fixes our problem because we can slide them in between, and we're not losing any data, right? Because if you think about it, in our category of sets, if we take the left uniter of A and we take the singleton set to be our monoidal unit, then say we're taking A, then we're just going to get A. And this is very isomorphic, right? So this is not a problem. Same thing for the right uniter. But we're still faced with this problem, where we need to shift the brackets. And this is where the last isomorphism that we need comes into play, which is called the associator, which takes A, B, C. So for any triple, what it does is it takes A cross B cross C, and we get A cross B cross C. How am I doing for time? Okay. So we have, and what this does is it just transforms our parentheses and fixes our problem. In our category of sets, what this does is it just shifts our brackets back and forth so we can actually now compose these objects. So in this example right here, we would just slide in an associator right here before we can, it's like rearranging our objects before we can actually apply the next transformation. Okay? So now let's look at what we have. What we have is a category that can do series composition, that can do parallel composition, that can braid objects, and that only needs to consider up to isomorphism. And now we've fixed pretty much all our problems regarding parallel stacking or vertical stacking. So we have 2 out of 3, and we're left with the last item on the list, which is called feedback. And feedback is, I'm going to keep this one clean so we can keep writing, but feedback is a very common thing in engineering that we see. It's when you basically take the output of a system and you just give it back so that we can use it for further computations. You've probably seen it. It looks like something like this. So we have information going this way, and our information is coming back. And this is a bit of a, again, we're encountered with a problem that we need to fix, because we've only presumed that our diagrams flow from left to right, or in only one direction. And here, we're going both ways. So how do we do that? Well, in comes dual objects. Because for any monoidal category, an object X has a dual, if there is an object X tick and 2 special morphisms called evaluation of X and co-evaluation of X. And these two, I always do it wrong, so let me just check. This one goes from X tick to X, X tick cross X to 1, the monoidal unit. And this one goes from 1 to X tick, I think. Yes. And these have to satisfy more conditions, obviously. But before we see these conditions, let's just write these out, okay? The evaluation of X goes from X tick cross X to 1. What we've said is that we don't really draw one because this is basically the same thing. So we can just not think about this. And our regular objects go from left to right. But our dual objects are what we're going to use to define feedback, so they go this way. So this morphism kind of does nothing, and it takes something that goes in and then spits it out this way. So what we do is we actually draw it like this. And now we've defined something that is corresponding to bending our wires in our diagram. And similarly, co-evaluation looks like this. So, there we go. And now we can get onto the conditions for these two objects, which are something that we call snake equations. And these two have to satisfy this, where this thing, am I doing this right? Yeah. Has to be equal to the identity over x tick. And this is a pretty cool condition because it's kind of topologically sound. Because if you think about a wire where you're bending it once and you bend it twice, then you can just kind of yank it this way and you just get a straight wire again, which is exactly what this does. And kind of analogously, we want this to hold. And so these are called snake or yanking, because you're basically yanking both ends. And so these are the snake or yanking equations, which are the conditions for dual objects to exist. And who says dual objects? Says dual morphisms. So if we have a morphism from x to y, then the dual morphism is f tick from y tick to x tick. So let's draw it out. F tick is like this. We're reading from left to right, so what we have is y tick, x tick, like this. And this is actually, if we consider this box, we define it by kind of sliding f into our yanking equation. So now you can observe this like this. This is equal, because here we have y tick, which goes this way, x tick, but we're bending x, so we can feed x and y into f. So what you do to define the dual morphism is you kind of slide it into the snake, and you get the dual morphism. And what's nice about this is that, I'm going to write this here. What's nice about this is that if you have f like this, then it's equal to f tick. Like, wait. No, that's not right. But if you take this way, you can slide down f this way. Let's just see. Like this. Then what you can do is slide down f tick here, right? You're just putting it right down here. And then you pull on the strings, and you get this. So this is kind of our sanity check for f tick. And what that means is that we can now slide morphisms along braiding and slide morphisms along the evaluation co-evaluation, which is the last thing that we needed to define feedback. I have 5 minutes, so I'm going to go real fast over this feedback thing. Feedback is what we call in category theory trace. It comes from linear algebra because if you think about your category of vector spaces, linear maps are matrices. The trace of a matrix is the sum of the eigenvalues. And effectively what it does is it's just a morphism from the underlying field to the underlying field. So the trace of an endomorphism f x to x, you write it diagrammatically like this. And what it does is if you close the box like this, then you see that you're just going from 1 to 1, right? Because here you have nothing, and here you have nothing, and you're kind of closing the loop of your system within itself. So let's extend this definition of trace now for more general morphisms, say f from x cross z to y cross z, right? Now what we can do is we actually trace over z because it's the only thing we can trace over. We can't feed y into x. So what we do is we, boom, using those two guys, we define the trace. You can write out the equations. That's not really the point. The point is to show you that these diagrams correspond to actual transformations and equations. So now that we have defined this trace, we can now successfully write any engineering diagram. And the structure behind this engineering diagram is called a traced monoidal category, which is a category with a monoidal product that you can braid, where the monoidal product is only up to isomorphism. You have the left and right uniters, you have dual objects, and then you have these traces for every defined over every morphisms of this type. And that sums it up. We have everything that we need now to formalize our engineering diagrams. And before we finish, now that we have this final object, what I'd like to do is show you kind of a quick taste of how you can prove things quite easily with this visual language. So, all right, 2 minutes. We're going to take a category of vector spaces, give it, the monoidal product is going to be the tensor product, or the direct sum, or anything you want, and then we're going to have these braiding operations, have the left and right uniters, and we're going to define two morphisms. So, category of vector spaces, we're going to have F be a morphism from V to W, and G be a morphism from W to V. And what we're going to do is, let's consider the trace of F composed with G, which is from V to V, right? So the way we drew this with our trace idea is like that closed loop. We have FG, our box, and we actually loop over this. And from series composition, we know that we can separate these two and have this. So we used our series composition idea to do this. And now we're going to use the dual morphism idea to write out that this is equal to F. And boom, we slide G down here, right? Because we're allowed to do that. We showed that it was equal for our definition of dual morphisms. So if we can slide it down one way, then we should be able to slide it up the other way, because this guy is going down and this guy is going up. And so now we just bring it back up. And we have GF, and we can basically do this step the other way, and we get G composed with F, this. And all of these are equal thanks to the semantics of the underlying category. And this is the trace of G composed F, which is kind of nice, because what we did is we basically proved a property, which is cyclicity of trace, using pictures, like using the toy for kids where you put beads around this. This is all we needed to prove cyclicity of trace, which is kind of awesome. And I think that's a very cool way to use category theory. It's to use it to visually think about things. And it's actually a very active research topic right now, where we're trying to develop, well, not we, but people are trying to develop categories to describe more and more complicated things in a very intuitive way, which kind of leads me back to what I was saying at the beginning, where it's very visual, and it captures how we like to think about things. And the point is that we can intuitively describe very abstract and complicated things. So yeah, that's why I really like category theory. Probably not a career prospect, because it's a bit too complicated and out there for me. But I think it's always nice to kind of enjoy the beauty of some things like this, which can be made very simple. I didn't go through any proofs of properties with you guys, because that would be too much, and it's too much for me as well. And I hope you enjoyed this, and that you kind of understood what I was trying to tell you during this presentation, and I hope you appreciated this final proof. So thank you for coming to my presentation. Do you have any questions? I'm sorry, you could have interrupted me for questions, but I forgot to say that.
Maybe.
Yeah?
Did I understand it correctly that we don't care too much then about, like with the braiding, which braid is going over the other?
Yeah, so in this, that's the thing, is like what we defined is a certain type of category, and there are other categories where we do care about braiding. And this is just not one of them, because you just consider, that's why I didn't do this. Like there's no way to braid over or under. We're just considering that you twist and then you untwist it by reapplying it. But yes, there are other categories where you consider these twists. Notably when you're doing, Hanmiru sent me a book on something I don't understand. It's topological quantum field theory, where you're like interested in how these things kind of twist, and the way they twist is different in both directions. So that would be a different, you would need kind of extra structure. But I thought that, yeah, this would probably be enough for today. So yeah, we don't care. Yeah?
How did you kind of get into all this stuff? Because you said we engineers,
Yeah. So last year I was talking with Ettore, and he told me that his dad does category theory, and I wanted to see what that meant. So I took this course at ETH, which is called Applied Compositional Thinking for Engineers, which is for mechanical engineers, which is kind of weird. It's a very small course, but like all of this basically is 2 lectures from the Applied Compositional Thinking course, and it's given by mathematics postdoc, and it's really interesting. And he makes it kind of very, quote, easy and more intuitive with these drawings, and then we use real life examples, like say you're using trace of this. This could be like a car motor, and you have the coupling and energy that's coming out, and you want to give it back. Like you actually use it for robotics. But yeah, it's very new, so it's not that in use yet. So it's an active field of research to see how we can put this to use. But there's already, as you can see, some cool properties that we can exploit.
Nice, thanks.
No problem. Yeah.
So, I mean, what you're saying basically is that at the level of engineering, it's more like a way of thinking rather than something that you can really prove things with.
Yeah, exactly. It's a way, there's this big thing that's called co-design, which is called compositional design. And what you do is you define these categories of motors and objects. And what category theory will do is it will offer you a way to put these, say you're considering like posets, where you only want monotone functions because your resources are mapped like monotonically to your functionality. And what you want is you want to ensure that you can, like, with this resource, do these two and get a functionality outwards without anything messing up and you like not having enough power to drive your car or stuff like that. So we actually do this a lot for autonomous vehicles because there's nobody to fix it if there's a problem. So what you want is you want like a very clear way to write this diagram where you will know that you can go from left to right without anything messing up, even including feedback, parallelism, braidings, all that stuff. So that was kind of how we motivated it, but I'm not knowledgeable in robotics, so I can't tell you kind of why, but the basic idea is with monotone functions, so you make sure that you're never, like, you never have not enough power for your car. All right. Well then, thank you for listening, and I guess I'll see you guys for lunch.